All right, welcome back to The Explainer. Today, we are literally unlocking a mathematical superpower. And hey, if you're thinking coordinate geometry is just about plotting, boring dots on graph paper, well, prepare to have your mind completely changed. We aren't just looking at dry math today. We're discovering a vibrant, dynamic tool that humans have used for thousands of years to map our physical reality. Whether we're navigating a massive, bustling city or just trying to design a layout for a brand new bedroom, the geometry we're exploring today is kind of like the invisible grid that holds our whole world together.
So I want you to really think about this question as we go through today's explainer, especially if you're tackling 9th grade math right now. How is it that ancient planners designing these massive cities, early astronomers charting the vast night sky, and a modern teenager named Shalini helping her brother, how did they all use the exact same mathematical concepts to map out their worlds? I mean, it sounds like a massive stretch, right? But I promise you, the connection is absolutely direct and super practical.
Okay, let's dive right into this. Section 1. Ancient Origins of Coordinates, a Global Journey. To really grasp coordinate geometry, we've got to travel way back in time to ancient Bharat. If we trace the timeline, as early as 3000 BCE, in the Sindhu-Saraswati civilization, city streets were constructed with this striking precision on north-south and east-west grids. Then, fast forward to 499 CE, and the brilliant mathematician Aryabhata is using similar coordinate systems to literally map the paths of stars. But, okay, here is the absolute crucial turning point. In 628 CE, Brahmagupta formalizes the notion of zero and negative numbers. And honestly, without this monumental leap, René Descartes wouldn't have been able to formalize the 2D Cartesian plane way later in 1637. So yeah, Brahmagupta's negative numbers, they basically made the modern map possible.
And the scale of this early coordinate use is just breathtaking. On one hand, you have these massive urban centers in the Sindhu-Saraswati civilization built at incredibly uniform distances, about 10 meters apart. It was a physical, walkable coordinate system where merchants could literally just count blocks to find a warehouse. And then, on the exact opposite extreme, you have Aryabhata looking up and replacing Greek chords with signs to track constellations across the ecliptic. From the dust of city streets all the way to the infinity of the night sky, it's the exact same grid-based logic. How cool is that?
All right, moving on to Section 2, Mapping Reality, Rion's Room.
Let's bring all this epic, thousands of years old history down to a super relatable human scale, something that directly impacts someone's life today. Let me introduce you to the story of a 9th grader named Shalini and her brother Riyan. So Shalini's family just moved to a new city, and for Riyan, who is visually impaired, settling into a completely new environment is, well, it's a really big challenge. So Shalini used what she learned in her 9th grade coordinate geometry class to actually help him out. She created a physical map using a rectangular grid. Scaling it at 1 centimeter to 1 foot, she fixed pins at key corners and ran thick wool right between them. This brilliant setup allowed Riyan to actually feel the directions and the whole layout of the bedroom floor with his fingers. She literally anchored real physical objects into a spatial framework.
Now, what's really interesting here is watching how this physical room transforms into formal mathematics. When we overlay the abstract math right onto the floor plan, the left wall of the room suddenly becomes our vertical y-axis, and the bottom floor edge becomes our horizontal x-axis. And just like that, every single piece of furniture, the bed, the wardrobe, the door, it suddenly has an exact, mathematically definable address on this 2D plane.
Which brings us to Section 3, the Cartesian Plane Explained.
So, we've seen it on a physical floor, right? Now let's break down the actual abstract concepts that build upon our room example. The absolute crucial starting point is the origin. In any 2D coordinate system, the horizontal x-axis and the vertical y-axis meet at a perfect right angle. That single point of intersection, that's called the origin, and its coordinates are exactly 0, 0. Think of this as your anchor. Every single distance in this entire 2D space is measured starting from this one singular point.
And when we want to pinpoint an object, we use a coordinate pair, x, y. Now, I cannot stress this enough. The order here matters immensely for pinpoint accuracy. The first number, the x-coordinate, always measures the perpendicular distance from the y-axis. Basically, it's just telling you how far right or left you need to go. Then, the second number, the y-coordinate, measures the distance up or down. I mean, if you swap them around, well, you might end up putting a wardrobe right in the middle of a doorway, and nobody wants that.
Next up, Section 4, Navigating the 4 Quadrants. But hey, what happens when our map actually needs to grow beyond just the positive numbers? And this brilliantly illustrates why we desperately need negative numbers. Let's consider Riyan's bathroom layout.
It actually sits to the left of our origin point. Remember, the left wall of the bedroom was our y-axis, meaning anything to the left of it completely forces the grid to use negative numbers along the x-axis. The showering area pushes right past the origin, deep into negative x coordinates. This is exactly why Brahmagupta's formalization of negative numbers back in 628 CE was so essential. I mean, without it, literally half of Rian's room would be mathematically unmappable.
So the axes naturally divide our plane into 4 parts, and we call these quadrants. You can kind of think of these positive and negative signs as a built-in GPS for any point in space. Quadrant I is where absolutely everything is positive, just like Rian's main bedroom. Then you have Quadrant 2, where the bathroom is. That one has a negative x but a positive y. Down in Quadrant 3 is where both x and y are negative. And finally, Quadrant 4 has a positive x but a negative y. Just by glancing at the signs of a coordinate pair, boom, you instantly know exactly which zone of the map you're currently in.
All right, moving into Section 5, calculating exact distances. Okay, now we've arrived at the true climax of our explainer. We know exactly how to plot points, sure, but how on earth do we figure out the exact mathematical distance between any two objects on our newly established grid? Look, if I ask you the distance between the origin and a point straight along the x-axis, you literally just count the units. Super easy. But what happens if the line between 2 points is completely diagonal and not parallel to the axes? Say we're measuring the distance from Rain's door straight across the room to the far corner of his bed. That line is definitely not parallel to either axis. So, how do we measure that?
Let's see how this builds, because to find this diagonal distance, we actually just break it down into 3 really simple steps that build directly on what you already know. First, we find the purely horizontal x distance between the 2 points. Second, we find the purely vertical y distance, and guess what? By doing just that, we've inadvertently created a right-angled triangle. So for step 3, we simply use the Baudrillard-Pythagoras theorem, which remember you already tackled in 8th grade, to calculate the hypotenuse, and that hypotenuse is our exact diagonal distance.
And that whole process gives us the famous distance formula. Now, I know it looks like pretty complicated algebra, the square root of x2 minus x1 squared plus y2 minus y1 squared. But please do not let those symbols intimidate you. Actually, scratch that. It's really just a direct mathematical translation of measuring your horizontal shifts, your vertical shifts, and plugging them straight into the Baudrillard-Pythagoras theorem. It works perfectly every single time, whether your numbers are positive or negative. Because as we know, squaring a negative number makes it positive anyway. It's just a beautiful, completely foolproof system.
Which leaves me with one final thought for you to ponder today. Imagine a world where Brahmagupta never formalized negative numbers. What would a system of coordinates even be like if we couldn't go left of the y-axis or below the x-axis? How heavily would that limit our ability to map modern cities, or code the video games we play, or even map a simple bedroom and bathroom layout for someone who really needs it? Coordinate geometry isn't just a bunch of numbers on a page. It is literally the mathematical framework of our reality. Keep exploring, and I'll see you in the next explainer.